All right, so to this point, we've covered three analytical techniques that people use to identify molecules. The first was IR, or infrared spectroscopy, and next was MS, or mass spectrometry, and now we're going to cover NMR. And NMR, like IR, is a form of spectroscopy. Okay, spelled correctly. Great. So this is another method for determining a molecule structure. This, I feel like, is the most important method and the method that will give us the most information. And as a result, we'll want to practice this one the most. What we're going to see for NMR is we're going to observe what's going on with the hydrogen atoms in a molecule. And since most of our molecules contain lots of hydrogen atoms, if you know about the hydrogen atoms, you know a lot about your molecule structure. There are other forms of NMR. So ours is proton NMR. There's C13 NMR, carbon NMR. There's fluorine NMR, there's phosphorus NMR. There are other variations of NMR, but we are exclusively going to focus on proton NMR. So what we're going to do is we're going to take our hydrogen atoms and we're going to excite them to a higher energy state with radio waves. So that's radio waves are part of the electromagnetic spectrum. It's a form of light, and so therefore this is a spectroscopic technique. And so that's the idea. We're going to excite our nuclei, and then we're going to see their excited states, and we're going to be able to get structural information on our molecules. Now, before we see examples of NMR spectrum, we'll see several of them. There are really three things that I want to talk about. One is this idea of chemical shift. So this is a spectrum you oftentimes won't even see explicitly drawn, the y-axis. But we're going to see peaks in our spectrum. And where these peaks fall on our x-axis is called the chemical shift. So this is the where of our peaks. Where do the peaks show up? So we're going to have to learn some chemical shift values. And because where these peaks show up is going to tell us a little bit about what each of these hydrogens is doing and what's attached around these hydrogens. Next, we're going to find out that these peaks are going to have certain shape. This is multiplicity. This is the idea of peak shape. So you can see here's a peak, and like these two peaks may actually be one signal, and it has a distinctive shape. That shape is also going to give us information. The peak multiplicity is going to give us information about that hydrogen. And then finally is integration, and this is simply the size of the peak. When we talk about the size, we are talking about the area of the peak. So it's not simply how tall it is, it's not simply how wide it is, it's that height and width combination. So it's the area of the peak. The larger the area, the more hydrogens are contributing to that signal. So this is going to tell us the number of hydrogens that we have. And collectively, these ideas, chemical shift, multiplicity, and integration, are going to be really valuable, and they're going to work together and give us a ton of information about our molecules. And if we use the other information we already have from infrared, that's knowing what types of functional groups we have present, and the molecular weight, which we get from the mass spectrum, then we can very often make accurate predictions about the structure of our molecules.